Ja, even checken. Wat is dit? Wat anders. Is terug? Ja. Okay, so before the coffee break, we dwelled into this 3D rigid body world with the orientation and so on. And our first goal now is to derive this relation between angular accelerations, angular speed, and torques. And we know it's a three-dimensional world, and there are three torques, and apparently also three angular accelerations, although I don't know what they are, but now let's see. So I made a nice definition of my body with a body fixed frame, and I can find any particle, mass particle. Why do I do that? Because I need the absolute accelerations in the end, because Newton tells me something like force is mass times acceleration, but only in an inertial world with reference to this reference frame. Well, how do I find this point? Again, with how do I find the point? I go to the center of mass, and then I go within the body to that point. Then I need to know the acceleration of this point. So how do I do? Well, differentiate. So the velocity is the velocity of the center of mass plus the velocity of this point within the body. And since this x prime I is a sort of constant in B, it doesn't change. Your nose stays relative to your head. We know what this speed is. It only can be because of the change in your orientation. And the change in your orientation, we sort of know from our other courses, we call that the angular speed. And the angular speed gives the change in your orientation with time. And then we know, oh yeah, that was omega cross xi. That was the way. Like when you want to calculate what is the speed at the skate in the 2D world, you said, oh, that's the speed at the center of mass plus the relative speed of A with relation to C, and that's just omega. Okay, so we now have a nice expression for our speed. But we need accelerations. So then we get, well, what is our acceleration? Well, it's of course the acceleration of the center of mass. And of course it is plus the angular acceleration cross product with these guys. But likewise here, this speed also changes. This speed changes because the body changes. And how does it change? Oh yeah, with omega cross omega cross xi. Now, if you do not feel secure about how this works, look in the first few chapters where Heike talks about the transport theorem, about rotating systems. There it's very clearly explained. But in an intuitive way, we have the position. The speed of the position is the change in position. Not, the thing doesn't change in length, so it's omega cross r. And then the acceleration is again angular acceleration plus this thing changes also in orientation, so we get again omega cross that thing. In hindsight, we recognize this. Oh yeah, this is the acceleration of the base point. This is due to angular acceleration, and this is omega squared times r in a sort of disguised form, because it's twice omega, so it's omega squared, and it's times distance, omega squared r, centrifugal terms. Well, that was not our purpose. Our purpose was to calculate the torques about the center of mass. So dm, and it's a three-dimensional thing, at c is of course, well, it is an inertia force, so it is acceleration in three directions, yeah, x double dot I, dmi. And then how do we find the torque in a general way? Well, again with the cross product. So the distance from the center of mass, and that was xi with the prime, cross this guy. And that is the torque. So again, going back to the picture, well, I shrink it a little bit. I have to shrink up again. So where does this come from? Well, we have an acceleration in some direction, and then times the mass is some inertia force, and then that is at a certain distance xi, and in general way a torque is distance cross product with the force, and this is then inertia force. Okay. The only thing now left is to put this expression here in and take the integral. So we say, well, mc is now the integral of, then we get the x prime I cross product with curly bracket. Then we have to repeat this whole guy, x double dot c plus omega dot cross xi prime plus omega cross omega brackets xi prime, close the curly bracket again. And again, we see terms which are constant, and let me underline them. Like this does not change with the point mass, the position of where the point mass is, and this is also constant within the whole body, and this guy and this guy. However, due to the cross products, here, and here, twice cross product, the thing becomes very complex, and actually there is no easy way to see what the outcome is. So as an exercise also in the book I say, well, use some symbolic toolbox and just write it out, and write out how these terms look like in just x, y, and z components in matrix form. Well, if you do that, then you finally come to the following conclusion, that so this cross product, especially this cross product. So the first part, this is not so interesting, right? Yeah, the first is not so interesting because again, this is a linear term, and this is a constant thing, and remember, all contributions with linear terms, they should be zero, right? Because that's how we defined the center of mass. So finally, this whole thing will drop out. Okay. Then let's focus at the second term. So the second term is x prime I cross product with omega dot cross product xi prime. Well, that's interesting. I want to put all the parts with the xi on one side of the equation and the omega, the constant parts on the other side. So I'm going to reorder this. So I'm going to write it as x prime I cross product with xi prime cross product omega dot. And if I do that, I have to put a minus sign in front of that because I changed the order of the cross product, and it means I'm not doing like this, but the other way around, so it's not plus but minus. It's just a change in sign. Now taking twice the cross product means, well, what does it mean? That is a complex thing. You have to write it out. And if you write it out, you will come to the conclusion that, well, these are terms with the x, y, and z, and this is with the omega, and the outcome is a 3 by 3 thing. So I can finally write it as a matrix times omega dot x, not omega, go back, omega dot y, omega dot c, right? Because this is just linear in these omega dots. And then within these brackets, I have this double cross product thing, which is super complex to do, but it turns out you get the following thing. You get, and then with the minus sign in front of it, you get, you get yi squared plus zi squared. And here we get xi squared plus zi squared, and here we get xi squared plus yi squared. Yeah, and it's all with a prime, because we are in this prime coordinate system. And that it's squared, it makes sense, because it's twice the cross product with x's, so x should be in a quadratic way present. Then what is with the off-diagonal terms? Well, let's take one. This one is going to be minus xi prime, yi prime, and this is minus xi prime, zi prime. And then here you can do the same. I get the same result. Yeah, the order is a little bit different. Yi prime, xi prime, and then minus yi prime, zi prime, and I get minus zi prime, xi prime, and minus zi prime, yi prime. Well, the first thing I notice is that this term is identical to this one, right? I can, if you can change the order of multiplication, which you can, so apparently this thing is symmetric. And when I take the integral of this guy, and I forget now a little bit about this guy, so this I shift away, and I do it times this dmi, then what do I get? Well, then I get by definition my mass moment of inertias at the CM. So you could also say that by definition my yxx is the integral of x yi squared plus zi squared dmi over the volume. And likewise for y and z. So meaning these two curly arrows mean that you have to do cyclic permutation. And cyclic permutation is, I write that the next letter after x is y, and the next letter after y is z, and the next letter after z is, what comes after z? X, I have to go around. X, y, z, and then so that is x. So apparently y is integral over the volume, this squared plus this squared. Yeah, but that means these double L's. So that is diagonal terms. And then the off-diagonal terms are, now we run into trouble. Historically, we say the inertia Ixy is defined as xi yi dmi over the volume. But see that there's a minus sign here in the matrix. That means if we define, and of course again with cyclic permutation, if we define what is the mass moment of inertia matrix in terms of these defined quantities, then we have to write this yxx, yii, yzz, so there's no discussion about that. But then we have to write here minus yxi minus yxz, and here minus yxi minus yzi minus yxz minus y. And it's symmetric. And this gives a lot of confusion with the minus. Some people, I think I did that in the past, defined this with a minus sign in front of here, and then there were no minuses here. And other people, like the book we have now, defines it with a plus here, and then the minuses are in the matrix. And if people with one idea read the text Bible with another idea, there's total confusion. So always be very careful when we talk about these off-diagonal terms. So we call this the mass moment of inertia matrix. Mass moment of inertia matrix. Now, what is so interesting about it? Well, it's symmetric. That is an interesting part, of course. It's probably positive definite. Distance squared times mass. We don't expect that finally to become negative. How can we see if it's positive definite? What do we look for then for a matrix? What are the characteristic values of a matrix? Eigenvalues, eh? And it's very unfortunate that they are called eigenvalues. Do you remember why they were called eigenvalues? Because of Professor Eigen, eh? Now they come from German. In Germany they started with Eigenwert, and then the Americans thought, well, that Eigen was probably a guy, so they said eigenvalue. Well, it should have been, of course, if we translate Eigenwert to an English name, then it probably would be characteristic value, because we write then the characteristic polynomial to find the eigenvalues. So the values then from the characteristic polynomial should be the characteristic values. But, well, that's how history goes. Unfortunately, it's called to Professor Eigen. Oh, no, there is no Professor Eigen. It's called eigenvalue. Very strange. So eigenvalue and eigenvectors. When we do that, when we transform two eigenvectors, transform two eigenvalues, what do we get? Then I put a star, because the coordinates are a bit different. It's transformed. But then the matrix has this form with only these numbers on the diagonals, and here all zeros. And in the book I did a bar on top of it. Okay, that's. And then these are the y bar xx and the y bar yy and the y bar zz are then the eigenvalues of the thing. And you'll see they will always be positive. Sometimes they can be zero when the size of an object is shrunken around one axis to zero, like the pen has almost no dimension in this direction. So the inertia for rotation is almost zero. But the other two, this and this one, they are large. And in this case, they are even identical. We have two identical eigenvalues. And it's actually pretty easy to find out what are the directions, because look at these integrals. They are x times y. So if we can find some symmetry somewhere, then we know, if there's a symmetry, then for the body, all the mass properties on the left are the same as on the right, then this whole thing will cancel out if y is left and right. So for axis of symmetry, these are zero. So these are these off-diagonal terms. They are then zero. So that is an easy way to find, what are the principal axes? Yeah, that's okay. So what are my principal axes? If I stand up, that's easier. Then I know one is this vertical, the long one. No. Then I have some symmetry. I'm almost symmetric. And I read somewhere that beauty is equal to symmetry. If you're very asymmetric, you're not very beautiful. They say. I don't know if it's true. But anyway, we are sort of symmetric. And then, so I expect that this and these are my principal axes, approximately. And where's my center of mass? Well, my mother already told me it's here. Your belly button, and that's the present you got from your mother. Here is your center of mass. It's really true. And then, where is it back and forth? Well, take about the middle somewhere. So now you know already where your center of mass is, you know where your principal axes are. What is my mass moment of inertia? I don't know. Well, I know it's too big, but I don't know the numbers. No idea. But you can guess your way around. Okay, so that's a little bit about mass moment of inertia and eigenvalues. But these equations, they are strange, right? I mean, let's write them again with these principal values. So the Newton-Euler equation, Newton-Euler with principal, we call them principal axes. Well, the Newton part, of course, is super simple. Some mass mx double, some forces y my double, and some forces z z double. And, well, maybe we say center of mass, c. That's now the Euler equation. So the sum of the torques about the x direction is, well, if we read the first part, then that's this, that's this mass moment of inertia times the omega dot in the x direction, right? Because we have all these zeros here. Plus, but now we are stuck because remember that we had omega cross I omega. And that was the part. And now we have to write that out in components. And if we do that, and I always make errors. Why is there a minus? Well, anyway, that is strange. II minus IZZ times omega I omega Z. And then the next one is sum of the torques is again in the y direction, of course, omega dot Z in the y plus, and then we have, well, you can almost cook it up, right? Through cyclic permutation, omega z, omega x. So there's no y. In the y equation, there's no y in these extra terms. And finally, the torque about the z is IZZ omega dot z. Oh, why did I write z here? It should be I. Plus yxx minus y omega x. So this part we are familiar with, and especially in the two-dimensional world. So remember, if we talk two-dimensional world, we only have this part. And then suddenly when we move from 2 to 3 dimensions, and zzz, the whole thing pops up, becomes 3 by 3, and we get all these extra terms. Well, sometimes terms disappear. So when do these terms disappear? That's an interesting question. So apparently, when we only have a rotation about one axis, either the z or the y or the x, right? Because then the other angular speeds are 0, and then these go away, these two. But they can also go away for special bodies. So, for instance, in the first equation, when does this always goes away? Well, when this is 0. When the mass moment of inertia about the y-axis is identical to the z-axis. So, like in the case of this pen, for instance. So there are, if we call the longitudinal axis the x, then this is the y and this is the z. Then the y and the z have the same mass moment of inertia. So this equation, this part will drop out. It's not present. But in the other parts it will be. The thing is tumbling on. Anyway, to get an idea about how do these equations work, I want to look at an example. And the example is very simple. It's about stable rotation, torque free. So what is the problem? I have some satellite in space, And the thing, these are solar panels. You all recognize these are solar panels. And the satellite has some angular speed, omega. And I'm curious, is that a stable configuration? So there are no torques in space. Well, there's a little bit wind from the sun and particles, but it's almost zero. So the sum of the torques in space is really zero. And then, given this satellite some initial speed, angular speed, will it stay that way, or will it start tumbling? And that's important because when it is in an orbit around Earth, I want to have the antennas orientated in the right direction, and I want to have the solar panels orientated in the same direction. So I really am interested in, will the orientation stay the same? How do we solve that? Well, let's assume we have these very simple principal axes. So we say that the inertia tensor is just a diagonal and with three different values like A, B, and C. Meaning it looks something like this: A, B, and C. And since I haven't given it any name, what is A, B, and C, then I can also assume that initially the omega is well, what shall we do? Around the first axis? Yeah, that's an omega around the first axis, and for the rest zero. And then the question is this stable? Will this remain always to rotate about that one axis? And in this case, it's the axis with the mass moment of inertia A. Well, to solve that, of course, and there are no external torques, we have to use the Euler equation of motion. So use Euler's equation of motion. And what does it say? Well, it says that the sum of the torques is equal to the mass moment of inertia times the angular acceleration plus omega cross I omega. But we are interested, of course, this is an initial speed, and we want to know how does it change. So we have to say, well, the angular speed is built up out of some initial speed plus a delta. There's a small change, and if that change decays in time, then it's okay, it's stable. If it explodes in time, then it's unstable, and if it oscillates like this, then it's oscillatory stable, we say. Likewise, for the omegas, for the torque, we say, oh yeah, so the sum of the applied torques is the initial torque plus the changes in the torques. No zero. So. And for the mass moment of inertia is what it is, right? There's no change in that. That's for a rigid body, that's a constant thing. Now we put these quantities in our equation, so we get m0 plus delta m equals to mass moment of inertia times, well, of course, if these are the speeds, then we have omega dot 0 plus delta omega dot plus, and then we get here complex omega 0 plus delta omega cross product with I times omega 0 plus delta. And then we just have to expand this equation. Now let's first get all the constant parts out of it. Well, let's expand it. So expanding this is super easy. I omega dot 0 plus I delta omega. Then this seems also simple because A plus B cross product with something is A cross product plus B cross product. Right? So you do omega cross product with I omega 0 plus delta omega plus, and then we get delta omega cross I omega 0 plus delta omega. Okie doke. Then finally we have to express these two more in detail, so I keep this one, plus. Of course, you could use a MATLAB symbolic or so to do this. It's not that hard. So cross product I omega 0 plus, and then the second part is omega 0 cross I delta omega plus, and then delta omega cross I omega 0 plus, and then the last one, delta omega cross I delta. And maybe I put brackets around this one. Okay. Now, first of all, if we look at all these terms, it's scales. So let's look at the variations delta omega to the power 0, meaning no deltas. What are the constant values? So that's m0. Then here's a delta, you forget that. Then I get I omega dot 0, and then I have to look here, I get plus omega 0 cross I omega 0. This is what we call the state about which we linearize, and this should hold. So if I put in all the numbers, then the results should be comply. Now we can check. You can check if that is okay. Is this a perfect initial configuration? And then the answer is yes, because we have no torques here, so we have 0. We assume that this omega 0 is some constant value, because we say there's a delta added to that one, so this is a 0. And then if you express this stuff, then you will see the outcome will be 0. So yeah, that's okay. The 0 order equation is correct. Then we take all variations of delta to the power of 1. That's the first order variation equation. So that tells us delta m, so the changes in torques which I apply are. Now the first part is the I delta omega. And then from this we have to subtract, we have to get the linear parts, and these are the two linear parts. So it's omega 0 cross I delta omega plus a delta omega cross I omega 0. So this is the most interesting equation which we will use. And what do we do with the delta omega squared? Well, there's only one term, and that we neglect that, because we are not we are not interested in higher order terms. We are only interested in linear terms, or we linearize our problem. So this is the equation we now can use to understand how will the angular acceleration change. Now, looking again at that equation, we're not going to add any torques, right? That's the idea. There are no torques in space and nothing will change. So the delta m is by definition 0. That's by definition. We have no extra torques. Then the conclusion is, this is our equation. Should be a dot here. So I delta omega dot plus omega 0, the initial one, times I delta omega plus delta omega cross I omega 0. So this is like, this is a first order differential equation in delta omega, right? We have pieces with delta omega and we have pieces with delta omega dot. So from this we can cook up what is our differential equation. Then we can look at the eigenvalues. We assume exponential motions. We look at the eigenvalues, and then we see, is the thing stable or unstable. But before we do that, we have to express this thing. We have to just calculate it. And an easy part is this part. So the I delta omega dot, that's super easy. Let me write for now what I use for delta omega. I used alpha, beta, gamma. This is shorthand notation. These are speeds. So the alpha, beta, gamma are speeds. They are changes in the speed. So Well, how does it look? I have A 0, 0, 0, B 0, 0, 0, C, and then times this alpha dot beta dot gamma dot. So that is super simple. Yeah? That is A alpha dot B beta dot C gamma dot. So that first part is not so hard. Then this one. Well, the omega cross that guy. So we get omega, which was omega 0, 0, cross. Then this guy, I delta omega. Well, looking at this, we already know, oh, that should be alpha, B, beta, C, gamma, right? And then the cross product. Well, that's also not so hard because there are a lot of zeros here. So 0 times, so the first is 0. Yo. The second is minus omega C gamma. And the last one is plus omega, last one is B beta. Mind you, gamma and beta are speeds. Very confusing. Don't want to write too much. Okay, so this part is resolved. Then the last one, that's alpha, beta, gamma, that's cross, and then I omega 0. That's super simple because we only have an omega here and here's 0, so that's A omega, and this is all 0. Yeah? So then the first is again 0. The second is a gamma A omega, yeah, and the last one is minus beta A omega, right? So now I have my ingredients. I have this term, this guy, I have this guy as this, and this and this. So we just add it all up. Yeah. So I get, I'll leave it like this because we're going to do eigenvalue analysis. Alpha dot, beta dot, gamma dot, plus, and then this guy, that was the first one, 0 minus C omega gamma, and this is plus B omega beta, and then here plus, and then I get 0, and I get a plus A omega gamma, and I get a minus A omega beta. It's 0. And of course, I can write this in a linear sense with, with alpha, beta, gamma. So again, I write A, B, C, I write alpha dot, beta dot, gamma dot, oops, and now I'm going to write this alpha, beta, gamma, because I want to have my first order differential equation. So extracting from these two vectors what it should be in the matrix, well, I know the first row is all zeros. Well, this is all zeros. But the first row should all be zeros because there is no contribution. 0, 0. Then the second row has something to do, well, only with gamma. So only with gamma. So there's a 0, 0, and then I get A minus C omega. A minus C omega times gamma. And then the last one only has something with beta. Yeah, so this is a 0 and that is a 0. And then it's B minus A omega. So yeah, a lot of zeros here and only these off-diagonal terms, which are not identical or not asymmetric or symmetric, just A minus C and B minus A, I don't know, times omega, of course. And here ABC. Now, if we assume that our delta omega is something, some amplitude times e to the power lambda t, we expect some exponential motions, that's the way how we solve that, then our delta omega dot is lambda a e to the power lambda t, and then of course we substitute that in the equation, and then we get an eigenvalue problem. So the eigenvalue problem we finally end up with is a lambda, and then plus 0, right? And then here also 0 zeros. And the second equation is 0, and then we get a b lambda plus 0. And then here we have a minus c omega. And then the last equation is a 0 here. Of course, we have this term, b minus a times omega. And then we end up with a c times lambda. And this, the determinant of the thing, should be 0, and that gives us the eigenvalue. Yeah, that's the way how it goes. Now, what is the determinant of the thing? Again, that's super simple because we have a lot of zeros in it. I don't know how you do it, but everybody has his trick. You could say it's this times the determinant of this guy, because this times the determinant of this is 0, and this times the determinant is 0. So it's a lambda times, and then we have to do the determinant of this guy, and that is b lambda times c lambda minus a minus c b minus a omega squared, right? That should be 0. Okay, well that looks not so complex. I have one 0 eigenvalue, and looking at the problem, that's super clear also that you have one, because you have two separate systems. You have here a system and here, and they are not connected. They are all zeros. So 1 0 eigenvalue, so this is lambda 0, and then the other one is b times c times lambda squared minus a minus c times b minus a omega squared is 0. And it's also not so hard to solve, because I know that the lambda equals a minus c times b minus a, that's okay. I divide that by bc, and then I omega, and I take the square root out of this, and I do plus or minus. Yeah, looks about right. So I have two solutions here, and then, what do I get? Well, if this if this is positive here under the square root, then I have a positive eigenvalue and a negative. So the negative eigenvalue, if it's negative, I have a nice decay going to 0. But if an eigenvalue is positive, I have this exponential growth. And as you can see, they always come in pairs. So if you have a damped system, if you have a decay, you also get the growth. So if this is positive, then it's unstable. And what if this is negative? What solution do we have then? So if a minus c times b minus a is less than 0, we get lambda as plus or minus I omega and then some number. Some number, I don't know which number. Or in other words, we get oscillatory motions. And they just oscillate a little bit. They don't damp out, they don't grow. Sort of oscillatory stable. We call that oscillatory stable. But for us, unstable, apparently, unstable is when a minus c times b minus a is positive. Well, when is that positive? Well, when a is larger than c and b is larger than a, or when a is less than c and b is less than a. Two cases, because you can have plus times plus and minus times minus. So if we rewrite this, we get BAC, and if we rewrite this, we get BAC. So we see it's unstable. When is it unstable? When A is in the middle. And A was the axis of rotation, right? Our omega was about A. So if you have some satellite in space and the rotation is about the middle axis, then the thing is unstable. That is what Euler tells us. Or in other words, the rotation about the largest mass moment of inertia axis or the smallest one, those are stable. Now this is a perfect satellite, right? 3 different mass moment of inertia. The short axis is this. The smallest value for mass moment of inertia is about this axis, and the largest is this, right? And the middle one is apparently this. So let's do an experiment. Let's launch our satellite. Now let's launch the satellite with a rotation about the largest mass moment of inertia. Then it should be stable. Pretty stable, right? I'm not so stable, but given the launch, pretty good. The small one, how do we do it? Looks okay. Yeah, I'm a bit nervous, of course. I cannot do this well. You are probably a lot better at this. But, okay, now this axis, right? The in-between axis. And I will really try my best. Nope. Well, we can sit here for hours. And for hours I will say no. And that's because maybe I'm clumsy. No. Because, no. It's the middle axis. So when you sit at home with your remote control, although you don't do that nowadays anymore, you sit behind your laptop, right? But anyway, some of you may sit behind a computer with a remote. You can try and see if you can get stable, but I bet you will not. And it has nothing to do with the beer you have been drinking or other things, or the age you have. It's because Euler tells you it's unstable. See you next week.